This is a situation that we had in the previous video. We have our hash table and we had put the first 5 items into there. And to get any one of them, it takes just one comparison. I don't have any collisions. If I want to find banana, my hash value is 6. I go to slot 6 and there it is. One comparison to find anything. It does not depend upon the size of n, and we call this order 1. There's no n involved here. So it's the most perfect thing that you can imagine, often unattainable, but that's the goal. If we were putting these things into a binary search tree, I put a tree down here with the first 5 things in. The first item I put in was pineapple and then grapefruit, etc. So I built my binary search tree here, and you can see it takes one comparison to find pineapple, 2 to find grapefruit, 3 to find apricot or passion fruit, and 4 to find banana. So this is not as good a structure as our hash table so far. But we wanted to put another 4 things into the hash table. And we wanted to put coconuts information, etc. And I have here their hash values according to the hash function that we are using. And we are going to do collision resolution with linear probing. And linear probing says if you're trying to put into the hash table and there's already something there, go to the next available slot. Okay, so the next one is coconut. Coconut's hash value is 7. I want to put this into 7, but 7 is occupied, so I'm going to put it into 8. And then I want orange. Orange is 6. 6 is occupied. The very next available one, going around to the top, would be 1. Apple is a 5. Apple can go into 5. And then mango is also 5. So mango cannot go in 5. It has to go into the next available one, which would be 3. So that is our hash table so far. It's no longer just one comparison to find anything. In fact, some of them are going to take quite a few. We'll count that in a minute. I put the remaining items into this binary search tree, and the number at the side of the key indicates the number of comparisons in order to find that particular key when it's in a binary search tree. And I wrote it out here for you. The average number of comparisons to find any object is the total number of comparisons divided by the number of objects, which in this case is 9. And that comes to 31 divided by 9. That should be a 9. 31 divided by 9. Let's look and see what happens in our hash table. So we ask ourselves, how many comparisons to find grapefruit? Okay, grapefruit is of hash value 0. It's in the correct place, so that number is 1. I'll write the number at the side here. 1. Orange is 6. Okay, so it should be here. Was it here? No, that's 1 comparison. Is it this one? No. 2. Is it coconut? No. 3, 4, 5. It takes 6 comparisons to find orange. How about passion fruit? Passion fruit is 2. It's in the correct place, so it took 1 comparison to find passion fruit. mango. Mango is a 5. 1, 2, 3, 4, 5, 6, 7, 8. It took 9 comparisons to find mango. Apple. Apple is a 5. It's in the right place. 1 comparison to find apple. Banana is a 6. That's in the right place. 1 to find banana. Apricot is a 7, and that's in the right place, so 1 to find apricot. Coconut is a 7, 1, 2 to find it. And pineapple is a 9, and that's in the correct place, so 1 to find a pineapple. So if I add these all up, adding these all up, the total is 23. So with the hash table and linear probing, the total number of comparisons to find everything is 23, which makes the average 23 divided by 9. Whereas with our binary search tree, the total was 31, making the average 31 divided by 9. So we can see that we're better, even with this very simplistic hash function, we are much better than a binary search tree. Of course, it's easy to find a really horrible hash function. Let's imagine it put everything, it gave every one of these a hash value of 3. We would be trying to put everything into the same slot, which would have lots of collisions, and it would be much worse than our binary search tree. So it very much depends on our hash function. We try to find the best hash function that we can and hope that we can get this average number of comparisons not only small, but independent of n. Well, we also want to know what's the average number of comparisons to find something that is not in our tree or in our hash table. Let's look at the tree first. Let's suppose that we have something that is not here. How many comparisons to find out that it is not here? Well, if it's not here and it's less than apple, it would be 1, 2, 3, 4, and oh, I've got a null pointer here. So 4, or check the null pointer, that would actually be 5 to know that something is not here. Similarly, here it would take 6 comparisons to find out there's something not here. We know that with a reasonably shaped binary search tree, the depth of it is log n. And so we hypothesize, or we assume actually, that the number of comparisons to find that something is not in our tree is log n plus 1. And that is also of order log n. With a hash table and linear probing, we can also count. We say, okay, if something is not there and it is of hash value 0, how many probes before I find out that it isn't there? And it's not a grapefruit, so that's 1. It's not an orange, 2. It's not a passion fruit, 3. Why am I going down like this? Because if there were collisions, it would be in the next one down. It's not a mango, 4. And I get to here and find out there's nothing. And that is actually a comparison. I'm comparing and finding there's nothing there. It took me 5 comparisons to find out that whatever I was looking for with hash value 0 is not in my table. 1, 2, 3, 4, 5. So what about something with hash value 1? It's not orange, that's one comparison. It's not passion fruit, that's two. It's not mango, that's three. And I find that there's nothing here, and that's my fourth comparison to find out that something with hash value 1 is not in my table. Okay, 2. One comparison, two comparisons, three comparisons. 3. One comparison, two comparisons. Hash value 4. I go there, the thing I'm looking for is not here, one comparison. Hash value 5. No, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 comparisons before I find that empty slot telling me that the thing I'm looking for is not in my table. Value 6. 1, 2, 3, 4, 5, 6, 7, 8, 9 before I find out it's not in my table. Value 7. 1, 2, 3, 4, 5, 6, 7, 8 before I find out it's not in my table. Value 8. 1, 2, 3, 4, 5, 6, 7. And value 9. 1, 2, 3, 4, 5, 6. All right, so now I have to add those up and divide by something. What am I dividing by? Before, I divided by 9 because that was the number of items that I had. Now I'm going to divide by 10 because that's the number of possible hash function values. So if I add up all of these numbers, I get 55. And with a hash table and linear probing, the total number of comparisons to find that something is not there is 55, which means that the average is 55 divided by 10. So whenever you have some sort of collision resolution, you have to do two things. You have to be able to draw the diagram, and you also have to be able to calculate the number of comparisons to find everything, the average number of comparisons to find an object, the total number of comparisons to find that something is not there, and the average of that. And the mistake that most students make is that they don't divide here by the total number of slots, which is the total number of possible hash values. They divide by the number of things in the list, which is not correct. You divide by the number of things in the list when you're talking about how to find everything that's in the list. But if you're saying that something isn't there, you're looking at all the possible hash values, and that is the size of your table.